Hello my friends, welcome back to a new video of IoT projects. The ESP32 microcontroller is great. I'm in love with it. In the last video of IoT project series we saw how it was possible to send data online using POST queries and online database to monitor any place with an available Wi-Fi connection. However, in many cases our Wi-Fi network is not going to be strong enough to arrive to our places of interest. Wi-Fi is an awesome technology, but you know better than me its limitations. It always wants us to be nearby. For instance, imagine that you live in a house with a garden and you want to monitor your vegetables garden. This is a personal case. The Wi-Fi connection may not be strong enough to allow the connections of the sensors installed outside. Or imagine a hydropower complex where, despite having internet in the hydropower plant, we want to monitor river water levels outside. In all those cases, to design a cost-effective network of sensors, we will need to go beyond the ESP32. But what if I say you that there is a magic combination of tools that allow us to transmit our data to the Wi-Fi hotspot despite the long distances? So here is where it comes handy LORA. LORA is a radio communication alternative that will allow us long-range transmissions with low power consumptions that can serve as a bridge between our sensors and the available Wi-Fi hotspot. Of course, any other radio frequency communication device could also work, but LoRa radio is known for being able to cover long distances, and two-way communication is usually simpler. So prepare your tools, because today we are going to build this bridge. We will build a LoRa connection to receive data from sensors installed at long distances from the Wi-Fi hotspot. To achieve our objective, we are going to design a small sensor network as an example, with two main components: a node that is going to measure the target variables on-site and transmit the information encrypted via radio, and a gateway, which is going to be a device installed in the Wi-Fi hotspot able to receive and unencrypt the radio information and after transmit it to an online database. For this project we are only going to build one node. However, the application is compatible with more nodes using a single gateway. For applications with more than one node, it's always necessary to transmit an identifier of the node or a name together with the information and check for the integrity of the message received to avoid cross-communications. Ideally, establishing a two-way communication between the node and the gateway, where, for example, the gateway asks for information to the nodes in a sequence using their identifier together with a new wake-up time before the nodes switches off. But this can be the topic of another video. Subscribe and let me know in the comments if you will be interested in more complex architectures. The components that we are going to use for this example are few. We are going to build the node with a Feather M0 board which integrates LoRa radio module, and we are going to measure temperature, humidity and pressure, perfect for gardening applications, using this small module which integrates two digital sensors: the AHT20 that measures temperature and humidity, and the BMP280 that measures pressure and temperature. For the gateway side, we will use our friend ESP32 microcontroller integrated in this chip board, and we will connect it to this small LoRa radio module from Adafruit. The connections are quite simple, but let's go briefly through them. Let's start describing the node. The board that we are going to use to make the node has already the LoRa module integrated. Therefore, we will only need to connect it to the digital sensor board by means of a E2C connection. For that, we will need to connect the sensor power to the 3.3 volt pin of the board, share the ground, the HDA pin and the SCL pin. Easy peasy. In addition, we will also connect an antenna and a battery together with a switch to power on and off the device. In this sense, we could also use an auto-powering circuit. For that, you can check the auto-powering video of the channel. Regarding the gateway, we will need to connect the LoRa radio module into the ESP32 board. For that, we will need to perform an ESP connection. First, we need to identify the correct pins in the ESP32 board. This can be done using the Arduino IDE. Power, ground, SCK, MISO, and MOSI are already predefined by default in the ESP32, while reset, CS, and G0 can be connected to any other digital pins of the board. Of course, we have to specify them in the code. As always, power of the module will be connected to the 3.3 volts pin, ground to ground, SCK by default to the pin G18, MISO to the pin G19, MOSI to the pin G23, and then we will select 3 more digital pins for the rest of the necessary connections. Pin G17 for the G0, pin G5 for the CS, and pin G16 for the reset. In the same way, we will also add an antenna to the device soldering a UFL connection to the LoRa module. So as you see, the connections are not difficult, so let's move to my favorite part, soldering. As I'm going to use the gateway in other projects, I will use an ice cover. Now that we have both circuits, let's write their code. We are going to focus in the circuit code, as the setup of Arduino environment and the web server is equal to the one described in our previous database video. Check the link in the description. The main difference in the setup is going to be that we need a new library, the Radiohead library. You can download the library together with the scripts used in this video in the description. We will start with the code of the node. First, we will copy and paste the Radiohead library into the Arduino library folder, and by doing so, Arduino ID will automatically recognize it the next time we open the ID. Arduino library folder is usually in your documents folder. The code is super simple. First, we include the libraries required for the digital sensors and the libraries for LoRa. We define a name for the node, in case that we are planning to use more than one, a data string to save the data, a sleep time to define the loop duration, sensor variables, the digital pins used for CS, reset and G0 connections in the LoRa module, the working frequency of LoRa, and the radio variables. Remember that the working frequency of LoRa depends on the country. In the setup, we activate the serial for debugging. We initiate the sensors, and we initiate the LoRa module. In the loop, first we get data from sensors, first humidity and temperature and after pressure. Then we join these values in a string separated by commas, and finishing with n keyword. Finishing with an n is not really necessary, but it can serve for checking the integrity of the transmissions. Then we convert the string into a char array for transmission, but before transmission we encrypt it. This function applies a XOR encryption algorithm, easy to implement and not super secure, but by selecting a long password, enough for our application. Finally, we send the encrypted data and we wait the defined sleep time. Once again, for real application, we will use an auto-powering circuit to completely switch off the circuit and the battery. Check the video. To upload the code, we will select the board and the COM port. And once it uploads, it will start immediately transmitting data. Let's move to the gateway code. The gateway code starts with the libraries required for the ESP32 Wi-Fi communications and the libraries required for the LoRa module. Then we define the variables, the Wi-Fi variables, the pins where we connected the CS, reset and the G0 pins of the LoRa module in the ESP32 board, the frequency, that is going to be the same as the nodes, and the radio variables. In the setup, we establish the Wi-Fi connection, we start the serial for debugging, and we start and configure the LoRa module. The loop is also simple. The gateway is always going to be listening for messages. The first commented code is for message transmission to the node, so we are not going to use it, but it is useful for defining two-way communications protocols for more advanced algorithms. If the module is available, we check if there are messages. These are saved in both variables. After, this message is unencrypted using the XOR function using the same password that in nodes, and we print the message via serial. We transform this buff array into a string, and we proceed to decompose the message in substrings to define our HTML post query. For that, we use the comma symbol between the variables, first the name, after the temperature, followed by humidity, and we finish with pressure, where we remove the end keyword in the final of the string. Once we decompose the message and we have the final URL, if the Wi-Fi is connected, we start the post of the data by accessing to the URL. And even if it's not mandatory, we check for the answer of the URL, finally ending the HTTP connection. This code is always checking for new data when available, independently of the node. Thus, it will work with multiple nodes, but do not forget to define a different name for each node. For uploading the code, we select the COM port and the board, and once it uploads, it will immediately start sending data to the same server that we defined in the previous video. The node is now situated in my garden, in a crappy box, and we are receiving data in the gateway and also in the online server, so everything works. With LoRa we can cover very long distances, even kilometers, but without testing I cannot believe it. Also, the antenna situation has to be good. Walls and trees can reduce drastically the coverage, so have always that in mind. So this is for now. All the code, libraries and connection drawings are available in the description. Hope you like it, and do not forget to support the channel and our work by subscribing, liking and commenting. See you soon!